In the last video we talked a little bit about how nuclei are held together, and today we're going to talk about how they can fall apart. We'll start in area that you're happy with, and then we're going to expand it into the stuff that makes this new for A level. So if I talk about the properties of radiation, you should hopefully already be aware of alpha, beta and gamma. Hopefully we know that alpha particles are 2 protons and 2 neutrons. Beta particles are basically a fast-moving electron or a fast-moving positron. That's a bit that's new, and we'll talk about that a bit more later. Gamma rays are just high-energy gamma rays, so they are just energy, so they're just a photon of energy. Alpha particles can be stopped by paper, beta particles aluminium, gamma particles lead. The range of alpha particles is about 1 to 2 centimeters, beta particles 15 centimeters to a meter, and gamma rays, because they are radiation, they're energy, they obey an inverse square law. Alpha are the most ionizing, beta in the middle, and gamma are the weakest. Hopefully the only thing that's new there is that I've thrown in the word positron. Everything else still holds true, and we can still ask you to talk about these properties. There'll be very similar questions to what they were at GCSE with these. So let's just look at a little more detail at each of these different types of radiation. So if we start with alpha, alpha radiation normally occurs in big nuclei. So you're going to find alpha radiation when the nuclei is very, very large. It needs to make a significant change to make itself stable. So an example would be uranium-238. We've already said an alpha particle is 2 protons, 2 neutrons, and after decay, the original nuclei is going to have its proton number decreased by 2 and its nucleon number decreased by 4. So in general, if I were to write an equation, if X is the element I start with, after decay it becomes a new element plus the alpha particle. So if we put the A and Z numbers on, they're going to look like that. So we'll start with A and Z of X. For Y, A will be 4 smaller, Z will be 2 smaller, and the alpha particle will have its numbers of 4 and 2. A specific example would be with uranium-238. So uranium-238 92 becomes thorium-234 90 plus the alpha particle. Now you can be asked to complete these equations, and mostly it would be a matter of putting in the numbers. They won't expect you to just know what the element will be. They might give you some options, so you have to pick the one that's got the right proton number, but they will give them to you. You don't need to know it off by heart. So one less thing you have to worry about. Don't have to memorize the entire periodic table. Okay, so that's alpha radiation, so that should just pretty much be what you were used to. Now beta gets a little bit different now, and beta decay is caused by the weak nuclear force, which is that fourth fundamental force that I told you about. Now you don't really need to know a lot about this one. This is the one that, as far as the exam board is concerned, you don't really know much about. I'm just going to tell you the very bare bones of it. And all you need to know is that the weak nuclear force causes beta decay. It's called weak because it's only significant in unstable nuclei. For stable nuclei, the strong force is much stronger, so it holds it together, which is why it's called the weak force. And it's just caused by something called W bosons. So W bosons get exchanged, and that leads to beta decay. So there are now 2 types of beta decay. We're going to start by looking at beta minus, which is the one that you are more familiar with. So beta minus occurs in nuclei that have too many neutrons. So an example of that is carbon-14. Beta particle is just a fast-moving electron. And what happens inside the nucleus is that a neutron turns into a proton and an electron. So we take a neutron, it becomes a proton and an electron. And the electron is what is emitted as the beta particle. Now the other thing we need to know is that at the same time an antineutrino is also emitted. So after decay, our original element, its proton number increases by 1, nucleon number remains unchanged. So in general, if we've got X as our original element, Y is the element it becomes because its proton number changed. The beta here is our fast-moving electron. You can put an E instead if you want, with an E minus. And then this is our anti-electron neutrino, sorry. You can just put the neutrino, so you can ignore the E and just put the anti-neutrino, but you do have to have at least an anti-neutrino. If you want to be perfectly correct, it is an anti-electron neutrino. So if we then just put our general numbers on, so if we started with A and Z for X, our beta particle has got to have 0 and -1. I know the -1 might seem weird, but you need to remember to put it on. And that is because our new element Y, it's going to have the numbers A and Z plus 1. But this is like an equation. This is a decay equation. So what I've got on the left has to match what's on the right, which is why if Z goes up by 1, the beta particle has to have a -1. And it's not a proton, so it's the opposite of a proton, so it's -1. However you remember it, just remember to put it on, because you won't get the marks if you don't put those numbers on. So a specific example then would be carbon-14 decaying into nitrogen whilst giving off that beta particle and the anti-electron neutrino. Okay, so I've said that what's happening here is that a neutron is decaying into a proton. Now I have also told you that neutrons and protons are made up of quarks. So we can actually think about this in more fundamental terms. We can talk about the beta minus decay as being a conversion between quarks. So what happens is that a down quark becomes an up quark. And at the same time, W minus boson is emitted, and then the W minus boson decays into the electron and the electron antineutrino. So basically I go from a down to an up, plus an electron, plus an anti-electron neutrino. There's absolutely no reason why that is floating, except that I had a fail and didn't spot it until now. So in terms of quarks, beta minus decay is a down to an up, plus an electron, plus an anti-electron neutrino. So let's have a look at the other option. So the other option was beta plus decay. Beta plus decay is the one that's the fast-moving positron that I talked about. In this case, a proton decays into a neutron and a positron. Positron is what gets emitted as the beta particle, and we also make a neutrino. So this time it's a neutrino that we make, not an antineutrino. After decay, our proton number decreases by 1. The nucleon number doesn't change. So if we just look at it for the general equation, I've got element X becomes element Y plus a beta plus particle plus an electron neutrino. So if we put the numbers in, we get AZ. This time my beta plus particle has to have a 1 number for its proton number, and again it's so that this adds up. So I've got A and Z minus 1 over here. So if we go for a specific example, I've got carbon-11, which becomes boron, plus my positron, plus my neutrino. Now, the hard thing you're going to have here is remembering which one is which. So, beta minus decay, you are making something negative because you're making the electron. Okay, and it has to balance. So if I'm making the negative electron, I must have started with something neutral because I'm going to make the positive and the negative. So I make the proton and the electron. And I made the electron, that's the new thing. So to balance the world, I have to make an anti-particle, so I make the anti-neutrino. In beta plus decay, I'm going to make something positive, so I'm going to be giving out the positron. So that means that I must have started with positive, because I'm going to end up with positive. So I start with a proton, which becomes a neutron. And I made the positron as the new thing, and that's antimatter. So I have to make some matter as well, just to keep out the world in balance. So that's why I make the neutrino. Okay. Just try and find a way to get it in your head. That's how I remember it, but whatever works. So again, we need to talk about this in terms of fundamental particles. And beta plus decay is a little weird. It's never going to happen just in a proton all on its own, because it's harder to make a neutron than it is to make a proton. It's basically just exactly the opposite of beta minus decay. So as far as we need to worry really, it's an up quark goes to a down quark plus the positron plus the neutrino. And it is as simple as that. But you do need to know that. So then, just a little word on these neutrinos, and I've talked about them before, but we'll just give you a little bit more. They are emitted with beta decay, and now beta decay from a particular nuclide always gives out a constant amount of energy. But the particles that are emitted, the electron or the positron, they can have different amounts of energy, because they could be emitted at different speeds. So the neutron soaks up the rest of that energy. It's there to make sure that that energy emitted is constant. It just means that it doesn't always, it sort of allows for you to balance it out, because your beta particle can be emitted at different speeds. And as I was saying before, with beta minus decay we always make an antineutrino, and with beta plus we always make the neutrino. And that's about balancing the amount of matter and antimatter that we're making. And as I said before, neutrinos are very difficult to detect because they have practically no mass and they have no charge. And as I said, we've got loads of them passing through us and the Earth even now, and we can't feel them at all, which, is probably a good thing. Probably don't want to feel the particles that are bombarding through you at every moment of the day. Okay, so that's beta. Next up we've got gamma radiation. And gamma radiation, as before, is just electromagnetic radiation emitted from the unstable nucleus. Most often occurs straight after alpha and beta, and it's when the daughter nuclei or the child nuclei has got excess energy from having decayed, and it then emits that energy, which drops it to a lower energy state, which just makes it more stable. And there is absolutely no change occurring in either the proton or the nucleon number as a result of gamma decay. Now, I've talked about a couple of things here, and I'm just going to throw one last piece of information in about all these decay chains. I've been talking a little bit about there being balance a lot, so I was saying we have to balance the amount of matter and antimatter we make. We have to balance the charge. So I have to have the same charge before and the same charge after. I was saying I have to have the same nucleon number before and the same nucleon number after. And that's because of conservation laws, which we've come across before. So conservation of charge is something we already knew about, so that shouldn't be new. The other one on my list is energy/mass. So I have to have the same amount of mass and energy at the beginning and the same amount of mass energy at the end. I have to have the same lepton number at the beginning and at the end. Now lepton number is easy. Leptons have a lepton number of 1. Antileptons have a lepton number of -1. And if it's not a lepton, it's 0. Same rules for baryon number. Has to have the same before and after. Baryon number, well, if it's baryon, it's +1. If it's an antibaryon, it's -1. If it's not a baryon, it's 0. So this is just something else to watch out for when we're looking at these equations. It can give you a little clue that something's gone wrong if these numbers don't balance. Oh, sorry about that. Okay, and that is it. That is it for this little section. So remember, got any questions, just ask when you see me.